We are saying hello from West Virginia. No, we are not saying hello from West Virginia. We're saying hello, but not from West Virginia. Oh my. Well, anyways, it is time for Joke of the Day, and I know that's your favorite part of the day, so let's get into it. What do you get when you cross a fish and an elephant? A fish and an elephant. What do you get? Swimming trunks. Oh my gosh, Joke of the Day is the best, isn't it? Okay, well, we are ready now to take a look at systems of linear equations in two variables. And we're going to look at how to solve our systems of linear equations. There are three ways to do it. One way is by graphing, another way is by substitution, and another way is by what's called elimination, sometimes called the addition method. And I'm going to have three separate videos for each of these methods. So this video is going to focus on the method of graphing in order to solve your system of equations. Now first, let's take a look at what a system even is. A system is a set of equations that can be solved simultaneously for a common solution. So let me flip this board around so you can see what a system looks like. I have three examples of systems here. Now I've got two equations there. That doesn't look anything weird at all to just simply have two equations. But what is weird is to have this little brace sitting here, and the brace is indicating those two equations are going together, and I am considering them to be one set. And I want to figure out the solution for the set. Now what you need to understand is, and I've mentioned it before, that whenever I graph this line, or the line represents the equation, and whenever I graph the line that represents that equation, that line is a picture representation of every single solution to that equation. Anything off the line is not a solution. Anything on the line is a solution. And remember, all of these points on this line, if I would take their coordinates, if I'd pick a point on the line and I'd pull its coordinates out and put the x coordinate here and the y coordinate here, if it's on this line, when I plug those coordinates in, it will create truth. If it's off the line or off the line and I plug those coordinates in, it will not create truth. So anything on that line not only is a solution to the equation, but it is the x and y coordinates for those particular points will create truth within the equation. So when I graph this line, that's a picture representation of all the solutions for that equation. When I graph this line, that's a picture representation of all the solutions for that equation. That is important in understanding the second point here, that when I am looking for the solution set to the system, I am looking for, let's think about this before you take a look at what's written. Think about this. If I graph one line and it looks like this, and everything on that line is a solution to that equation, and then I graph a second line and it sits like this, and everything on this line is a solution to that equation, and I am looking for the common solution, then where's the common solution going to sit? Yes, right here where my wrists are, because that's the point of intersection. This point where my wrists are, that is a solution to this equation. It's as well a solution to this equation. So this is the common solution to both. So when I'm looking for that solution set, I'm looking for the intersection of the solution sets for each equation. In other words, the intersection of the graphs. So when this happens, we can have two types of systems. One type is what we call a consistent system. A consistent system says, yep, we have solutions. It is a set that has solutions. Now there's two ways that this could happen. One way is to say, okay, I've got a line going this way, and then I've got another line going this way. These are what we call intersecting lines. And intersecting lines are going to be a consistent system because intersecting lines, as you can see in the picture, there we go, intersecting lines definitely have a point of intersection, and this is where the solution is going to sit. Now notice that if they are straight lines and we don't have any curves going on, but if they are straight lines, they're only going to intersect at how many points? Yes, one point right here. Now if there's curves, it's potential, see, if it's a curve, I'm going to intersect right here, and then I'm going to intersect right here again. But we're not doing curves right now, we're doing linear. So there will be two lines involved here. But my point is, if they're intersecting lines, you're going to have one solution and that's it. Now, how do we express that solution set? Well, that solution set has a point in it. Now we always use braces to indicate that we're talking about a set. And what we're going to put in this set is that point, or its coordinates. So whatever those coordinates are for that point, I'm not going to always put an x, y, but whatever the coordinates are for that point, they will go in there. That will be my solution set. Now, let's consider another situation. What if, and remember, this is a set that has solutions. What if we graph one line here, and then when we go and we graph the second line, what if the second line sits right on top of it? Now remember, my solution set is going to be the intersection of the graphs. So in this type of picture here, where's the intersection of the graphs? Yes, every single point on that line is an intersection. So if every single point on the line is an intersection, what we have is same line, first off, but like we said, every point on the line is a solution. So how many solutions do we have then? Remember, in this situation we had one. How many do we have? Now remember, this arrow means the line's going forever in this direction, forever. The arrow means the line's going forever in this direction. How many solutions will we have? Yes, infinitely many. However, this only tells me how many solutions we've got. It doesn't tell me what the solutions are. Remember up here, this told me I had one solution, but it didn't tell me what the solution was. I needed to know, what is that solution? Well, here, what's the solution? The solution is every single point that's on that line. Now, how do we describe that? Remember, we're talking about a solution set, so I'm going to use braces to indicate set again. And what I want to say is every point on the line is a solution. Well, what I'm going to do then is I'm going to this time use a generic x, y. I'm not going to put any numbers in there at all. But this says the set of all points. And then I'm going to put a colon. And the colon simply says the set of all points that satisfy. And then what I'm going to do is put one of the equations that are in that system. And it doesn't matter which equation you choose to put in here, because both equations are going to mean the exact same line. They both represent the same line. We'll see an example of that, but this is how it goes. Now, this is what we call a dependent system, and it is called a dependent system because the position of the second line depends on where the first line's set. Because remember, they are the same line. Now, we also, this is what we call a consistent system. Again, a system that definitely has solutions, but there's another idea that could happen. What if we graph one of the lines and it goes like this, and we graph the other line and it goes like this, and they are parallel to each other? Remember, parallel means it's got the same type of tilt. So if they are parallel to each other, where is that point of intersection going to be? You're right, there's no point of intersection because parallel lines are never going to cross, never going to touch, never going to intersect, it's never going to happen. And remember, that is where my solution set is, at that point of intersection. So if I have parallel lines, then that means that I have no points of intersection, in other words, no solutions. And this is what we call an inconsistent system. Because an inconsistent system is a set that has no solutions to it. None. As opposed to, like I said, your consistent system that says, yeah, I've got some solutions in there. I'm just not sure if I have only one solution or infinitely many solutions, but I've got them. This one says, nope, no solutions at all. And so every time that you have an inconsistent system, that will always mean parallel lines. That's the only way to not have any points of intersection on your lines. But here again, how do we express that solution set? Well, remember, the braces mean set, and I've got to figure out what am I going to put in here. I need to put the point of intersection in here, but we said there was no point of intersection, so what am I going to put in there? You're right, nothing. This is what we call the empty set, because it is a set that has nothing in it. Now, there's another way that we can express this, and it's what's called the null set, N-U-L-L-S-E-T. It's a sloppy U, forgive me. There we go, N-U-L-L-S-E-T. This is the null set. The null set means empty set. They mean the very same thing. What you definitely don't want to do, and a lot of people do this, you don't want to put your empty set like this and then put the null set in it. It's because, frankly, your braces is kind of like a bag. And so what happens is, you've got your braces here, and my bag has nothing in it. It's like I'm carrying a purse, and I've got nothing inside my bag. But this indicates, okay, braces says I have a bag, and now what's happening is I'm putting another bag inside of it. It's kind of like saying, okay, here is my bag, and so if I have the empty set, see, my set is empty. But that is the same thing as this. Now, if I'm trying to express this, this is, say, the braces indicates here's my bag that's empty, but now what I'm going to do is I'm going to put another bag inside of it. This bag as well is empty, but I'm going to put it inside. And see, that's not at all what I'm trying to say. This is not an empty set because now my set actually has something in it. So I don't want to do this by any means, either this or this. So this is how your system of equations works. This is how you're going to determine what your solution to your system is. Again, remembering, I am looking for the common solution. That common solution is going to be the intersection of the graphs. That's really the main point. So let's take a look at some examples here. And you saw that I had 3 of them for us to examine. So what I'm going to do is I'm going to solve each of these systems by graphing. Now you know how to graph lines. So what I'm going to do is I'm going to take this first equation, I'm going to graph that line. I can either do my x and my y-intercepts, or I can turn it into slope-intercept. I'm going to go ahead and turn this one into slope-intercept because all I have to do to make that happen is subtract that x. And that will get that y by itself. Now when I subtract the x, I get a negative x plus 4. Now I can graph that line on this 2D coordinate plane. Here's my y-intercept of 4. Put it on first. Remember, the slope is a great counting tool, fantastic counting tool, but I need to have a place to count from. So always start with your y-intercept. Now my slope is -1, rise over run, so I need to have that denominator. And now that means I'm going to go down 1, right 1. So I'll come down 1, right 1. There we go, is my second point. And I'm going to connect them and just pray, pray, pray that it is straight, because you never know with me if it's going to be a straight line. So this is the line that represents the equation x plus y equals 4. Now I'm going to graph my second line, and on this one I think what I'll do is try to put it in as well as a slope-intercept form. So the first thing that I'm going to do is subtract that 3x, and when I do I get a negative 2y equals negative 3x plus 7. And then what I'm going to do is I'm going to divide both sides by negative 2. When I divide this side by negative 2, I'm going to get a positive 3 halves x. And when I divide this by a negative 2, I'm going to get a negative 7 halves, which does not reduce, does not simplify, so I'm going to leave it alone. Now remember, my y-intercept of negative 7 halves, whoa, that's going to be a little bit tricky. But this is the equivalent of negative 3.5. So that means on my y-axis, I'm going to come down 1, 2, 3.5 to sit right here. From that point, I'm going to use my slope of 3 halves, which means I'm going to go up 3, right 2. So from here, I'm going to go up 1, 2, 3, and then go to the right 2, landing me right here at this half mark right here. Now I'm going to connect those, and again, pray, pray, pray that it's straight, because I cannot draw a straight line to save my life. All right, so this is the graph for the equation 3x minus 2y equals 7. And now remember, what I'm doing here is I'm looking for that point of intersection right here. That's where they cross. What are the coordinates for that point of intersection? Well, it appears that those coordinates are going to be 3, 1. So that is going to be my solution to my system, 3, 1. Now, I need to check it, because think about this. If this is a solution to the system, what it means is I should be able to put the 3 and the 1 here, come up with truth. I should as well be able to put the 3 and the 1 here, and again come up with truth. If I come up with truth in both equations, yes, this is a solution to the system. But if I plug it in one of the two and it creates truth, but it does not create truth in the other one, it's not a solution to the system. It's only a solution to the one in which it creates truth. So we do need to check and make sure that this works in both equations. So if I put the 3 and the 1 here, 3 plus 1 is 4. Yes, that works. It creates truth. Put the 3 and a 1 in here. 3 times 3 is 9. 2 times 1 is 2. 9 minus 2 is 7. It works. So this is, in fact, a solution not just to this, but it is a solution to the system. All right, let's test out our another example. Notice these two are already in slope-intercept form. Whew, half my work is done. So I'm going to go ahead and graph these on that 2D coordinate plane. And I've got my y-intercept of -1. And my slope here of 3, rise over 1. So I'm going to put it over 1. That means come up 3, 1, 2, 3, go to the right one, landing me right here. I'm going to connect those two and again pray that it's straight. Whoo, with me, you never know. Y equals 3x minus 1. And then I'm going to go and I'm going to graph the second line. Here is my y-intercept of 6, 2, 4, 6. And again, my slope of 3. Now remember, I said that meant up 3, right 1. Well, I'm kind of running out of room, so I could go down 3, left 1. Because if I go down 3, left 1, -3 over -1 is still going to be a positive 1. Or sorry, not a positive 1, but a positive 3. So it'll still be the same slope. So I'm going to come down 1, 2, 3, and I'm going to go to the left one like this. And I'm going to connect those two. And again, oh my gosh, pray that it's straight. And so this is y equals 3x plus 6. What do you notice about the lines? It does appear that they are parallel. Now, how can I check to make sure that they're parallel? What do we know about parallel lines? Yes, they have the same slope. Because remember, slope tells me the tilt of the line. And if they're going to be parallel, they have to tilt in the same way. Do they have the same slope? Yes, they do. So I do know that they are, in fact, parallel lines. But what does that mean about my solution to the system? Remember, I'm looking for the point of intersection. So in this picture, where is the point of intersection? If they're parallel, you're right, I'm not going to have a point of intersection. Remember, this was the case where I either have the empty set that looks like this, or most people like to do this. Most people like to put the null set in there. Both of them are indicating there is no solution. I have a set that's empty. All right, let's take a look at our last example. So in this one, I think what I'll do, instead of putting it into that slope-intercept form, I'm going to practice a little bit with the x and the y intercepts. So I'm going to take my top equation here, my 2x plus 4y equals 8, and I'm going to get my x-intercept and I'm going to get my y-intercept. Now remember, to get the x-intercept, I make my y 0. So that means that I'm going to put a 0 right here. And remember, when I put a 0 right here, that entire term is now gone. Totally gone, because 0 times anything is just a 0. So I'm left with a 2x equals 8. And when I divide by 2, I get 4. So that gives me a point, and put it in coordinate form. Very important that you know where the 0 goes. I get a coordinate of 4, 0. And so that's going to be right here. But now I need to get the y-intercept for it. And the y-intercept means let's make the x 0. So now I'm going to take this equation right here and I'm going to make the x 0. And again, when I put a 0 right there, 0 times anything is 0. This term is now completely gone. I am left with a 4y equals 8. And when I divide both sides by 4, I get a 2, giving me the point 0, 2. Again, because I made the x 0, and when I did the y came out to be a 2. So that gives me the point 0, 2 sitting here. And now there's the 2 points that it takes to make that line. So I'm going to go ahead and graph the line. Once again, praying that it's straight with me. Oh my gosh, you just never know. I do not have a steady hand at all. But this is the line for 2x plus 4y equals 8. So now I'm going to take my second equation. I'm going to do the same thing. I'm going to go ahead and get that x and y intercepts. So to get that x-intercept, once again, what I'm going to do is make the y 0. So I'm going to put a 0 right here, and like we said before, when I put the 0 there, that term is completely gone because 0 times anything is 0. I'm left with a 6x equals 24, and when I divide by 6, I get x equals 4, giving me the point 4, 0, because I made the y 0, And that point, wow, sits right there. Well, looking like that might be a point of intersection. Okay, so let's check out this out and let's get that y-intercept. So with the y-intercept, remember what I have to do is I have to make the x 0. So I'm going to take this term right here, take that x, put a 0 in its place, and once again, 6 times 0 is 0. This term is now completely gone. I'm left with a 12y equals 24. So when I divide both sides by 12, I get 2, giving me the point 0, 2, because I made the x 0. And oh my goodness, it sits right there. And when I connect those two, wow, it is the exact same line. So not only is this 2x plus 4y equals 8, it is as well 6x plus 12y equals 24. But remember, the whole idea here is I need to figure out my solution to the set. Remember, the solution to the set is the point of intersection. Well, where's the point of intersection? Yes, every single point on the line is a point of intersection. Now, remember, how do I express that? Well, I'm talking about a set, so I'm going to use braces. And I'm going to say all the points, so I'm going to use my generic x, y. And I'm going to say all the points that satisfy, that's what the colon means. And remember, it satisfies either this equation or this equation because you saw those two equations represented the very same line. So it really doesn't matter which of these two equations I write in. As a habit, I tend to pick the top one, but it sincerely does not matter which one you pick. And cap it off with the end brace. So let me reiterate. This means the set, that's what the braces mean, the set of all points, x comma y, is going to indicate all points that satisfy, that's what the colon means, and one of the two equations because they mean the same thing. So, hopefully this helps you with understanding how to solve your systems of linear equations by graphing. Remember, the whole point is you are looking for the solution set, and that solution set is the common solution. It's going to be the intersection of the graphs. So graph each of the lines, find that point of intersection. If they're parallel, you're not going to have a point of intersection, so you have no solution. Again, do not write this. Write either this or this. If they are same line, then every single point on the line is going to be your solution set. And so this is how you write that. And then if they're intersecting, put that point of intersection in as your solution. I hope that helps. Have a great day.